Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Ernest Orlando Lawrence's invention of the cyclotron in 1931 marked a pivotal moment in the history of nuclear physics. His creation, elegantly simple in its initial conception, provided physicists with a means to accelerate charged particles to energies previously unattainable, thereby facilitating groundbreaking experiments in nuclear transmutation and the exploration of the atomic nucleus. This essay will delve into the historical context surrounding the cyclotron's inception, the innovative principles underlying its operation, its immediate impact on scientific research, its subsequent evolution and widespread adoption, critiques and revisions that shaped its development into the sophisticated accelerators of the intellectual landscape preceding Lawrence's invention was ripe with both promise and frustration. The early 20th century witnessed a flurry of discoveries concerning the structure of the atom, culminating in Rutherford's model of a dense, positively charged nucleus surrounded by orbiting electrons. However, probing the nucleus itself proved to be an exceedingly challenging endeavor. Natural sources of alpha particles, such as radium, provided energetic projectiles, yet their intensity and energy were limited. Artificial acceleration of particles offered a potentially more controlled and powerful alternative, but earlier attempts, such as those by Cockcroft and Walton, were hampered by the technical difficulties of generating high voltages. These early experiments, while significant, were limited in their achievable energies, typically in the hundreds of kiloelectronvolts range. A method for achieving significantly higher energies, while avoiding the cumbersome high-voltage equipment, was, therefore, in substantial demand. The conceptual breakthrough that led to the cyclotron arose from Lawrence's realization that charged particles could be accelerated to high energies by repeatedly subjecting them to a relatively small accelerating voltage. This idea, inspired partly by a conversation with Norwegian engineer Rolf Weidre regarding linear accelerators, dispensed with the direct application of immense voltages, a technological hurdle proving difficult to surmount. Instead, Lawrence envisioned a device in which ions would be accelerated in a spiral path by a constant magnetic field, passing through the same accelerating voltage multiple times. The first cyclotron, a relatively small device a mere few inches in diameter, consisted of two hollow, semicircular electrodes called Ds, placed within a uniform magnetic field. An alternating voltage was applied between the Ds, creating an electric field in the gap separating them. Ions, typically protons, were injected into the center of the cyclotron and accelerated across the gap. The magnetic field then bent their trajectory into a circular path. As the ions completed each semicircle, they returned to the gap, where the alternating voltage had reversed, accelerating them again. This process repeated itself, with the ions gaining energy and spiraling outwards with increasing radii until they reached the periphery of the cyclotron, where they could be extracted and directed towards a TA. The fundamental principle governing the cyclotron's operation relies on the relationship between the magnetic force on a charged particle and its velocity. The magnetic force, given by the Lorentz force law, which states that the force on a charged particle is equal to the charge of the particle multiplied by the cross product of its velocity and the magnetic field, which is mathematically represented as F equals qv cross b. This force causes the particle to move in a circular path with a radius proportional to its momentum and inversely proportional to the magnetic field strength. Critically, the time it takes for the ion to complete one semicircle is independent of its velocity, provided the particle is not moving at relativistic speeds. This isochronous property allows the alternating voltage to be kept at a fixed frequency, ensuring that the ions are always accelerated as they cross the gap between the Ds. The frequency F, known as Cyclotron frequency, given by F equals qb over 2 pi m, which the charge of the ion, being the magnetic field strength and energy of the. Upon its initial operation at the University of California, Berkeley, the cyclotron immediately showcased its potential. Lawrence and his team, including graduate students like M. Stanley Livingston, rapidly improved the design, building successively larger and more powerful machines. These early cyclotrons were instrumental in producing artificial radioisotopes, which found immediate applications in medicine and biology. For instance, radioactive isotopes of phosphorus and iodine, created through cyclotron bombardment, were employed as tracers to study metabolic processes and diagnose thyroid disorders. The ability to produce these isotopes on demand in relatively large quantities revolutionized these fields, opening up new avenues of research and The impact of the cyclotron extended far beyond medical applications. It became an indispensable tool for nuclear physicists, enabling them to probe the structure of the nucleus with unprecedented precision. By bombarding various elements with accelerated protons, deuterons, and alpha particles, researchers were able to induce nuclear reactions and create new, previously unknown isotopes. These experiments provided invaluable data on nuclear forces, energy levels, and reaction mechanisms, contributing significantly to the development of nuclear theory. The success of the Berkeley cyclotron spurred the construction of similar machines at other universities and research institutions around the world. Physicists recognized the potential of this technology, and cyclotrons quickly became essential equipment for nuclear research. As the demand for higher energies grew, Lawrence and his colleagues continued to push the boundaries of cyclotron technology. One significant development was the introduction of the synchrocyclotron, which addressed the limitation imposed by the relativistic mass increase of ions at higher energies. As ions approach the speed of light, their mass increases, causing them to fall out of synchronism with the fixed frequency of the alternating voltage. The synchrocyclotron overcomes this problem by modulating the frequency of the accelerating voltage, adjusting it to compensate for the relativistic mass inc. The synchrocyclotron, while capable of achieving higher energies than the classical cyclotron, suffered from a reduced beam intensity due to the frequency modulation. This limitation led to the development of the isochronous cyclotron, which employs shaped magnetic fields to maintain a constant orbital frequency even at relativistic speeds. Isochronous cyclotrons, also known as sector-focusing cyclotrons, utilize magnetic fields that vary with azimuthal angle, creating alternating regions of higher and lower field strength. These variations provide additional focusing forces that counteract the defocusing effects of the relativistic mass increase, allowing for continuous beam operation at high energies. Throughout its evolution, the cyclotron has faced its share of critiques and challenges. One early criticism concerned the relatively low energies achievable with the classical cyclotron due to relativistic effects. The development of the synchrocyclotron and the isochronous cyclotron addressed this limitation, but at the cost of increased complexity and, in the case of the synchrocyclotron, reduced beam intensity. Another challenge lay in the extraction of the accelerated ions from the cyclotron. Early extraction methods were inefficient, resulting in significant beam losses. Over time, more sophisticated extraction techniques were developed, involving the use of electrostatic deflectors and magnetic channels to steer the ions out of the cyclotron with minimal loss. The legacy of the cyclotron extends far beyond its direct applications in nuclear physics and medicine. It served as a crucial stepping stone in the development of more advanced particle accelerators, such as synchrotrons and colliders, which are now the workhorses of high-energy physics research. The principles of radio frequency acceleration, magnetic confinement, and beam focusing, pioneered in the cyclotron, are fundamental to the operation of these modern accelerators. Moreover, the cyclotron fostered a culture of innovation and collaboration in physics, bringing together scientists and engineers from diverse backgrounds to tackle challenging technical problems. Lawrence's radiation laboratory at Berkeley became a model for large-scale, interdisciplinary research centers, which have played a vital role in advancing scientific knowledge. The development of the cyclotron also had a profound impact on the relationship between science and society. It exemplified the potential of scientific research to address pressing societal needs, from medical diagnostics and treatment to energy production and national defense. The success of the Manhattan Project during World War II, which relied heavily on cyclotron technology for the production of plutonium, further solidified the link between scientific research and national security. This legacy continues to shape science policy today, with governments around the world investing heavily in scientific research and development. In conclusion, Ernest Lawrence's invention of the cyclotron represents a watershed moment in the history of nuclear physics. Its elegant design, combined with its transformative impact on scientific research and its subsequent evolution into more advanced accelerator technologies, secures its place as a monumental achievement. The cyclotron not only provided physicists with a powerful tool for exploring the atomic nucleus, but also stimulated innovation, fostered collaboration, and shaped the relationship between science and society in profound ways. Its story serves as a testament to the power of human ingenuity and the enduring quest to understand the fundamental laws of nature. The cyclotron's influence resonates even today, informing the principles and designs of cutting-edge particle accelerators that delve ever deeper into the mysteries of the universe. In a way, Lawrence's initial tabletop device indirectly powers the most advanced experiments into the fundamental nature of reality itself.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.